Assalamu alaikum. Hello, everyone. Today we are going to have a talk by Dr. Khalid Khalaf. The talk will be on semiconductor research, semiconductors research to production, learning and challenges. Let me first start with the introduction about Dr. Khalid. Dr. Khalid received his bachelor and master's and PhD degrees in electrical engineering from Ain Shams University in Cairo, Egypt, and Delft University of Technology in Netherlands, and Vrije University Brussels in Belgium in 2005, 2010, 2016, respectively. In 2005, he was employed by Scenario Design Services in Cairo, Egypt, and spent 2 years at Infineon Technologies in Munich, Germany. And also he joined the famous IMEC in Belgium in 2009 for 10 years, working on millimeter wave CMOS ICs for high-speed wireless applications, where he led the latest 60 gigahertz beamforming and digital transmitters ICs. In 2019, he co-founded Farotech in Belgium, which is an IMEC spin-off focusing on delivering chip and phased array antenna module products for 60 gigahertz fixed wireless access and consumer applications. Dr. Khalaf is an author and co-author of more than 40 publications, including conferences and journal papers, patents, and 3 books. Thank you, Dr. Khalid, and please go ahead. The floor is yours.
Thank you, Ahmed. Thanks a lot. Thanks everybody for your interest in joining. I'll now share my screen. You see it?
Yes, it's visible.
So I'll move to full screen.
So just for everybody, we'll leave the Q&A until the end. Just maybe 5 to 10 minutes before the end of the lecture, we receive the Q&A. Thank you. Go ahead.
Thank you. So yeah, we all know semiconductors are everywhere in our life, all the way from mobile phones, cars, medical equipment, TVs, satellite, and laptops. Just to have a feeling of how big the market of semiconductor is. So only the first 5 companies in the semiconductor market, they have a market cap of around $2.5 trillion. If we actually recently, Apple started also doing their own semiconductor, fabricating their own and designing their own. So if we just add it, just to get a feeling how big it is, if we add it to the total market cap of the semiconductor industry, it goes to about 8 trillion, which is even exceeding the oil market cap. In the past 50 years, the semiconductor technology have advanced quite exponentially in a very amazing increase and advancements of the technology. Moore's law, which is a famous law, said that the number of transistors will be doubling every 2 years. And almost amazingly, the demand, the growing global demand and the quality research offered over the previous 50 years have led to huge, incredible improvements and advancements in the semiconductor technology. So in the next few slides, I'm going to walk you through the research versus production, just to give you like snippets and feeling of it. Transition through a startup incubation phase, some challenges facing a startup company, and examples semiconductor companies. So what is the research about? The research is mostly about proving an idea can work. So you make an idea, you try it out, you see that it's working, you test it even once, you're happy with the result, you go publish it. While production is actually a little bit different, it's actually a lot more different. It's about showing that this idea is always working. And always here means really over a lot of statistical distribution. A lot of temperatures, under a lot of variability. You need to think about Monte Carlo analysis every time you think about sensitivity. You need to think about yield analysis, stress analysis, reliability, repeatability, reproducibility, stability. You need about robustness, failure modes, DFM, DFT, ATE machines. So you go into really a production environment, automation environment. You need to ship in a certain volume. You need to always ensure that your test time is small, is very small in seconds, that you're guaranteeing very minimal return or failures or customer returns, usually measured in ppm, part per million. A lot of statistics, a lot of mathematics. That's all what you will actually feel in production or in a production environment. So what are the elements that you need to have in order to think about, okay, this is the moment I need to think about moving to a startup. So you need to have a technology mature enough to go to a market. You actually need to have a relevant market for the technology that you have. It shouldn't be too early, shouldn't be too late. You need to have a team that is motivated enough to drive the startup into all the challenges it will come through. You need to have some access to funding through family, friends, incubation, investments, loans. You need to have also an ecosystem, some kind of a customer base, industry experience around you, talent pool that you can access, a supply chain. These are just examples of the elements that you need to have in order to think about, okay, this is the right moment for going to a startup and actually commercializing the research I'm working on. So how difficult this step is, which is commercializing a research and moving to a production or a startup. So it's sometimes overestimated and sometimes underestimated. So it's usually too overestimated by people outside the field. They think it's a lot of technological barrier. Startup success rate is usually 10-20%, and so on. It's sometimes seen too easy for people who were engaged in the research. They contributed to a lot of several innovations in the field, and they don't have a lot of industrial and startup experience. So where is the truth? The reality is a little bit in between. It's quite difficult, but not impossible. You need to have the right position and puzzling pieces of the technology, market, team, funding, and ecosystem. You need to have the right strategy for addressing those challenges, and you need to have the right industry relevant, both technical and commercial expertise, accessible near you so that you don't fall into easy traps. So next we'll move to the incubation phase. So during the incubation phase, it's a phase where you secured some time, and that's usually a few months, where you need to focus on, okay, do I really start now investing more money into it, more effort into it, or it's worthless? Because usually in the research, you don't have a lot of time during the research environment, you're quite busy with your measurements, your designs, and so on. And you need to take a phase where you need to assess the opportunity in more seriously. And this phase, you need to secure some of your efforts, some of the money to work a few months, for instance, to get all of the elements concrete. For example, those are the elements that you need to take through this incubation phase. You need to work on a market analysis. You need to work on a competitive analysis. You need to create a business model. You see how you're going to sell. You need to start reaching your customers, and that's very important. Before really taking off and spending a lot of effort and a lot of money, you need to already start looking and reaching out to your potential customers. For example, if they're starting getting interested, you start getting recommendation letters, which will help you further in further stages of the company. You need to get your prototype ready. So this incubation phase needs also to ensure that you get a prototype, which can also help you in the future steps of the company. The next is going to be valuation and fundraising. And of course, in fundraising, you will be using all the previous elements to convince someone to work beside you. So next we'll be moving to some of the challenges that you can expect to see. So here I'm going to talk mainly about market challenges, technology challenges, funding challenges, team and ecosystem challenges. So I'll start with the market challenge because I think it's actually one of the very important and critical challenges out of all of them. So usually you have a research, you're not the only one in the world doing that research. And then you want to think about, okay, I want to commercialize it. So how do I going to compete? How is the market going to adopt my technology? So usually there are two extremes. One extreme is that you're working on a market that is very saturated. For example, a mobile market, it has about 200 mobile companies in the world, very large, valued at 400 billion in 2021. Almost most of the world population already use the technology, and it's very highly competitive. On the other side of the spectrum, you can see markets that are very small. Markets that are like like a space travel, for example, commercial space travel. There are 6 companies working on it, still valued at 400 million. Only 38 humans used it, so there is a high adoption risk. So normally you get to choose between a very high competitive market or a very high adoption risk market. So how to address this challenge? For example, there is a strategy called beachhead market, which is usually suitable for startups. So you have limited resources, you have limited people, limited time, you need to go fast to the market. So you start by focusing all your resources and effort on a niche market. So a market that is small, not necessarily the one that you want to work on at the end, because it's not the one that you're going to give you the largest revenue, but it's still small enough to get you standing on your feet. And you have your roadmap for the next markets and the next products. So this helps establishing your startup, standing on your foot, and then you can continue from there to more competitive markets. What about the technology challenge? Of course, when you come out of the research, usually the technology is not mature enough for your prototypes, for your MVPs. So you need to spend some time and effort working on that. It's also usually not protected enough. For example, not enough patents, not enough patent scopes, something like that. And of course, you start risking the time to market and the high cost barriers of translating this prototype into a more mature MVP that you can use into the market. So here, for example, here it's like representing a lot of gaps that you have in the technology and a little protection that you have in the current technology. So a good research strategy can actually help reducing this gap. So the gap that you're talking about is the time to market, which is important, because if you come to the market too late, you lose most of the competitive edge, you lose most of the market. It's very difficult to bridge. And of course, the cost is usually a very large barrier. So a good research strategy can help reducing this gap by working closely with industry. So not just doing research for research, but actually working close with industry so that you can be ensuring that you're helping or solving problems that are realistic in the market. You also get to know your specifications. What is the most important parts that people or industries are concerned about? Also, another point in the research is that you work on a higher level of abstraction. So you don't only focus on the pain problem, but you also try to increase your level of abstraction. You do, instead of, at least for a prototype, you get to a usable system that you kind of prototype and show. So this can improve or reduce the gap for a future spin-off, for instance, or a startup to include or adopt this technology and bring it into the market. K for patentability, which is not usually very obvious for people in research who try to put all their efforts on patent on publishing. which is also possible, and you don't have to reduce your effort in publishing, but you can always patent something just before publishing and you get it secure. So what about product strategies that can also reduce the gap to the market? So good collaboration with customers, and that's very important so that you exactly know your main critical points, and you ignore or reduce into the priority the points that are least or less important. That's very important because usually we have very limited resources and in terms of time and cost. So you focus on the key specs, which are the customer pains, and you drop the rest. So it means that you do not work for a perfect solution. You don't have to work for a perfect solution. It will still have some gaps, but it's less than what you had before, and it's good enough for the customers to start with. With a roadmap and future development or improvement, you can always get your pass-through. You also need to think about sacrificing the cost for the time to market and risk in the technology risk in the first phase. So don't always try to think about how do I make it the most cost-effective solution in order to increase the most revenue or profit out of it. In the first phase, it's most important to focus on the performance, on the reliability, and this is really what the customer wants. So even if you reduce your margin or profits, that's always fine in the first place or in the first phase, and then in the next phase you try to optimize the cost for higher profitability. It's also important to think about the patenting strategy. So in patents there are several ways to address this, and one of the very good ways is to only focus about the regions that are very critical for your business, for your market. And there is also a bundling strategy which helps delaying the costs of the patents and actually keeping it strategically open for a longer period of time, so that you can also change the dynamics of it and address the competition or the changes in the market as the business goes. So what about the next challenge? The next challenge is about the funding, and there are several funding sources that you can think about, all the way from family, incubators, investors, VCs, loans, and you can think about using your personal relationships. You can think about using industry-relevant conferences where you can demo your technology and get to know your investors. You can think about incubators that can help assisting this, can provide support. Also accelerators that can usually provide support, like business support, but also exposure and relationships with possible investors and funding resources. One of the very important challenges that you face during the fundraising is the budgeting. So assume that you have raised a certain budget, and then usually the budget that you have is tied to a certain milestone that you need to achieve, and it's usually a technical or a business milestone. Assume that you work on the milestone and you get it done, closed before the funding is over. Then you're successful in achieving your milestone. Your fund is sufficient. You have still remaining resources so that you can work on the roadmap and the next fund or the next fund phase. You have increased your valuation, and that's very important that your fund is actually enough and exceeds the milestone that you work on. Simply because if you take more time to implement the milestone and to work on it, usually you run out of cash, usually your valuation is reduced, usually you get to dilution, sometimes even end up by bankruptcy. So even if you have a very good technology, a very good team, and you just miss your milestone, you may end up in very big problems. So what's the workaround on that? What's the solution of that? Just to be more generous in getting your budget. So of course, generous enough. So a value like 2x your initial budget is not so large. Of course, 10x or 100x is so extreme. Just take the worst case scenarios in the planning, translate any risk you see into planning margins, take additional margins. Many new factors could always pop up that you didn't know about. because of the non-experience that you have, or the limited one. So what about the next challenge? The next challenge is about the team challenge. So usually you need to find a team that covers different aspects of the company needs, all the way from technical, business, and industry experience into the team. The team needs to have some level of harmony, some level of common goals, some level of shared values, respect, and ways to resolve disputes. Need to agree on role distribution. In the first phase, you need to agree on the assignments and the initial company structure. So this is just an example of a company structure that is shown successful for small dynamic environments, also large companies. So usually it works like on two levels or axes. The vertical axis is the resource levels, and the horizontal axis is the project levels. So you get to start from the vertical level or the resource level, which usually starts with the board of directors, for example, a CEO, some group or department or team that is closer to the supply chain, a core team that works on the engineering and the technology itself, and a marketing team or a product management team that works mostly with the customers and interfacing with the customers. Usually within engineering, you have the design or the core technology team and the production team, and anyone in the resource axis can actually be picked and leading a project axis. So you need to have the hierarchy in the vertical axis, and then you can also have a leadership in the project axis. So what about the next challenge is about the ecosystem. So you need to also be having a good access and be close, preferably in actually physical space to your customer base, or to some of the customers at least. This usually helps better understanding the customer requirements, better building a relationship, which is very critical in the first phase of a startup. You need to also be close to similar industries or similar companies, just to have access to expertise. You need to be close to a talent pool. So, for example, good universities, good research institutes, educational institutes that can provide a good skill set for your startup. You need to be also close to the supply chain. It usually reduces the costs. It usually gets you better understanding all the details of the supply chain, which is important to get you get your handle over all the details and the production details. So for the how to build this, it's actually actually everyone has a responsibility to reach out to the relevant parties. So the ecosystem normally includes industries, governments, investors, universities, and it's of course centralized by the society. All of these need to work to have a mutual relationship, needs to work in a mutual understanding. Let's say that's the ideal situation. Usually, in many cases, people just focus on one link. For example, universities working with industry, and with that going to spin off, they then face issues with government or face issues with funding, or and so on. So working only on one or two links of those is usually making it more difficult, and you need to think about building relationships and with all the ecosystem parties. So in the next, I'll just show some examples from semiconductor companies, how they started and how they ended. So, for example, this is here I talk about TSMC. It started from the government. It's a government effort to work in collaboration with industry, utilizing an existing research institute, building over this knowledge, and working on TSMC. it was in the 35 years ago. They invested a value of about 400 million. And over the time, it growed until it reached about 400 billion market cap. So it has a revenue of 70 billion per year, and the valuation increased almost 1,000x over the past 35 years. This is another company, which is, for example, ARM. It started with a lot of ups and downs and a lot of persistence and perseverance from the founders working on different research and different trials to commercialize electronics when it started, until reaching let's say a phase where Apple invested using tools. So you get a multi-part sides. You also get some help from the government at one point. And it created a value of about 10 million only, also about 25 years ago. And currently it grew and succeeded to a valuation of about 32 billion, which had an exit to SoftBank in Japan. So those are big companies, very old companies. So what about reality, something close in time and small enough maybe to a scale that we can work on? So this is also another company that started only 5 years ago from Columbia University. It took a small investment, relatively small for what the silicon or semiconductor companies usually get. It only worked for 5 years, and it had an exit of about $135 million. So that's about 5 to 50x, depending on the phase in which the investment started. So by this I would like to thank you, and thank you for all your attention, and I think I have some good time for having some discussion and Q&A.